Welcome to second lecture in our short video lecture series on the column buckling and the stability of columns. The first video was an introductory video in which we discussed the stability of equilibrium, and in that lecture video we looked at three different types of equilibrium: stable, unstable, and neutral equilibrium. Today is our second lecture and we will look at the derivation of Euler buckling load. So before starting today's lecture, what we discussed in our previous lecture was that when a long column is subjected to some axial compressive load, then a phenomenon occurs in it which is known as buckling, and that buckling means the lateral deflection of those columns. So if we suppose that this is a column, and in this column a certain axial compressive load P is acting, then this axial compressive load causes the development of axial compressive stresses in these columns, which is given by the value of load divided by the area of these columns. As we increase this value of R, a certain point is reached when the value of P is equal to PCR, which is the critical value of the load. And at this value, critical value of the load, whenever we give a certain displacement to the column, then the column tends to move further and further away from the position of initial equilibrium, and thus it tends to fail due to buckling. This process is what we call as buckling in our previous chapter. So compressive members are frequently used in our structures, and these members lose their stability before the material crosses by yielding if the length is significant. If our columns are short, then the primary mode of failure is by crossing due to the acting loads. However, if our column is long, instead of failing by crossing, these generally fail due to buckling. So load carrying capacity of our compressive members is very less as compared to the load carrying capacity of the same type of tensile member. And in today's lecture, we will look at how to derive the Euler buckling load. Euler is the name of the person who derived the value of this buckling load. His name was Leonhard Euler, and he derived the value of this buckling load during the 18th century. We will look at this derivation today. So let's start with today's lecture. Okay, let me repeat again in a short sentence what we discussed in our previous class. When this value of load P is less than the value of the critical load, our column is in a stable equilibrium in this straight condition. When the value of load is equal to the critical value of the load, then our column is in neutral equilibrium in either the straight portion or a slightly bent position. But when the value of load exceeds the value of this critical load, then the column is unstable in the straight position and will also buckle under the slightest disturbance. So we have considered here a column which is pinned at both ends, that is end A and end B. We are going to describe the stability of a real column. A real column in the sense that in our previous lecture, when we discussed the buckling nature of our column, we discussed that we have two massless rods or massless bars AB and BC, and the point of flexibility of these two bars was located at the middle portion. That means these two bars were also joined by a pin connection at this central point. So this was an ideal condition of concentrated elasticity, but now since we are dealing with the stability of a real column, we will consider the condition of distributed flexibility or distributed elasticity. That means there is no any particular pin connection as in our previous assumption. Instead, our column can bend or buckle from any point along the length of this column. So we have an ideal column here. Ideal in the sense that we have some assumptions which we will discuss in the next slide. And these are pin connected at both ends, and a load is acting as a compressive load in our column, which is P. So initially the value of P is less than the value of the critical load PCR, such that our column is in a condition of stable equilibrium. Then as we increase the value of this load and the magnitude of that load is equal to the value of the critical load, then our column has buckled here in our second figure, and this shows the buckled configuration. So if we give a slight displacement to this column, for example, we have given a displacement to the left side in this second figure, that is figure number B, under the effect of a load which is equal to the value of the critical load, then our column is now in a state of neutral equilibrium. We have selected the coordinate axis as x in the vertical direction and y in the horizontal direction. The displacement is represented as Vx, and the displacement currently is in the left side. So if we draw a free body diagram of this buckled configuration of the entire column, then we get a free body diagram as shown here. The initial length is now changed to some value L star, since the column is now curved in xy plane. We suppose that the reaction forces at points A and B are Ax, Ay, and By. Finally, if we cut a section along somewhere in this column at a distance x, and we see the free body diagram of a partial column, this is the free body diagram that you will see. If we use the conditions of static equilibrium, then you can find that the vertical reaction at point A, that is Ax, is P in the upward direction. The axial force acting along this column at a distance x is again P. The displacement at the position here is Vx, and the moment acting along this column is Mx. So you can use the equations of static equilibrium to determine these reaction forces and the internal forces. So why did we call this ideal column? In our next lectures, we will study the different values of Euler critical load or the buckling load for other cases other than this ideal case. But for today, we are looking at the derivation of the conditions of an ideal column. So there are four assumptions here. The first is that the column is initially perfectly straight and it is made of linearly elastic material. Remember, we are dealing with the condition of linearly elastic. The column is free to rotate at its end about frictionless pins. That is, it is restrained like a simply supported beam. So if you rotate this simply supported beam 90 degree anti-clockwise, then you will get the column that we have assumed here. So it is restrained like a simply supported beam. Each pin passes through the centroid of the cross section. The column is symmetric about the xy plane, and any lateral deflection of the column takes place in the xy plane. That is, we have assumed here that the x-axis is vertical and the y-axis is horizontal. So all the deflection that is taking place in our column is taking place in this xy plane here. Our z-plane is perpendicular to the plane of paper or perpendicular to the plane of this screen here. And we suppose that there is no deflection of the column in this z-axis. Rather, all the deflections lie in the xy plane. And the column is loaded by an axial compressive force P applied by the pins. And that axial compressive force, the line of action of this axial compressive force is along the axis of our columns and passes through the centroid of this column. So these are the assumptions that we take for the derivation of the buckling load for an ideal column. So let me draw the diagram that we saw in our previous slide of the free body diagram. This is point A. The reaction at point A is P. The axial force acting at a distance x from this A is also P. And the moment we have considered mx here. So if we use the principle of static equilibrium and take the summation of moments about A equals to 0, then you will find that If the horizontal deflection of this point at a distance x is Vx, then the moment due to this force P and the moment moment Mx are both acting in the anticlockwise direction. So what we can write is Mx plus P times Vx equals to 0. And if we take this term to the right hand side, then we get Mx equals to minus P into Vx. Now substitute this value of Mx into our deflection curve equation, that is the moment curvature equation, which is given by Ei v double prime x equals m. You may have also written this equation as Ei d square y by dx square equals to m. So this is the symbol for the slope of our moment curvature equation, which is represented as v double prime x. Since Vx is our displacement, v double prime x is represented as d square y by dx square. So substituting this value of Mx in this equation, we get Ei v double prime x is Mx and Mx equals to minus P into Vx. If we take this minus P into Vx to the left hand side, then this becomes our governing differential equation. Ei v double prime x into plus P into Vx equals to 0. So this is the differential equation that governs the deflected shape of a pin-ended column. Remember, now we are discussing the case of a pin-ended column. For other end connections or other end conditions such as hinged column or fixed column, what will happen to the value of critical buckling load we will see in our upcoming lectures. But for now it is a pin-ended column. Now this governing differential equation that we have got, it is a homogeneous linear second order ordinary differential equation. You are already familiar with these terms here. It is homogeneous because the right hand side is equal to 0. This is a linear equation and this is a second order differential equation. And this governing differential equation has these two boundary conditions. The boundary condition depends on the type of end restraints that we have provided here. Since it is our pin-ended column, if this is our column that we are currently discussing about, the displacement at x equals to 0 is also 0. That means there is no horizontal displacement at this point, neither there is horizontal displacement at a distance L from this point. So V0, that means V at L equals to 0 is equal to 0 and V at L equals to L is also equal to 0. So these two will be our boundary conditions. Now using these boundary conditions, we have to solve for the value or solve for this differential equation. Let's solve it in our next slide. So what we got was Ei into V double prime x plus P into Vx equals to 0. Since we are considering uniform columns, the Ei is constant along the whole length. So divide both sides by Ei, what we get is V double prime x plus P by Ei into Vx equals to 0. So this governing differential equation becomes an ordinary differential equation with constant coefficients. If it were a non-uniform column, a column with varying cross-section or a tapered cross-section, whatever it may be, then Ei, this flexural rigidity, would not be constant along the whole length of the column. But since we are considering uniform columns for now, Ei is constant. So we will get this equation. Suppose P by Ei is represented as lambda square, then your equation becomes V double prime plus lambda square V equals to 0. This is similar to the differential equation of a simple harmonic motion. So the general solution to this differential equation is given by this equation here. You should already know the general solution to this differential equation based on your undergraduate mathematics course. C1 sin lambda x plus C2 cos lambda x equals to Vx. This is our solution. Now what we have to do is we have to use the boundary condition to determine the value of these constants C1 and C2. To do that, first let's use this boundary condition here. Put the value of x equals to 0. Then sine 0 is 0, so this whole terms becomes 0. Cos 0 equals 1. So from this we will get C2 equals to V0, which is given as 0. So C2 equals to 0. And if you put x equals to L in the same equation, then VL, which is again equal to 0, is given as. Now since C2 equals to 0, this term will be 0. The remaining term will be C1 sine lambda instead of x, L. So C1 sine lambda L equals to 0. Now let's look here. This left hand term will be equal to 0 under two conditions, when either C1 equals to 0 or sine lambda L equals to 0. But remember, we already have C2 equals to 0, so our solution has reduced to Vx equals to C1 sine lambda x. If our C1 is again 0, then Vx will simply be 0, and this will turn out to be a trivial solution. This will in fact just represent the straight condition of your column. There will be no buckling. So to ignore or to remove this trivial solution, C1 cannot be 0, so that sine lambda L now should be equal to 0. The same thing is written here now. Sine lambda n times L equals to 0. Why n times L? Why we have used this suffix here? Because we are going to get the general value of this lambda L. The simplest condition will be that sine lambda L equal to sine 0 such that lambda L equals to 0. Now lambda, what we have taken is P by EI. Since the length cannot be 0 here, lambda should be 0, and for lambda to be 0, the load acting on the column should be 0. So this is not the case that we are trying to enforce here. Instead, we are trying to get the value of P. So we again have to ignore this simplest case in which sine lambda L equals to 0 such that lambda L equals to 0. Instead, we get the general values of lambda L other than for this 0, so that lambda L equals to n pi, lambda n L, let's say, such that lambda n is given now by n pi by L. N will start not from 0 but from 1, 2, 3 and so on. So this is the general value of lambda. Now if you substitute this general value of lambda in our equation, lambda equals to P by EI, such that P is now given as lambda EI. So the nth value of P is given by Pn. Lambda will be, sorry, this is lambda square here. So lambda square is now n square pi square by L square into EI. We just squared this value here. So this now gives us the value of the load acting on the column for the nth mode. Similarly, the deflection curve that corresponds to each load Pn is obtained as C into sine n pi x by L. Since we have Vx is given as C into sine lambda x, instead of lambda, we write n pi by L. This gives us the deflection curve or the equation of the deflection curve. Now this is also known as the mode shape or the buckling mode. That means the shape into which our column is deflected based on the load Pn. So now to find the value of the critical load. The value of P at which buckling will actually occur is the smallest value given by the equation for Pn. So if we want to get the smallest value of Pn, then we have to put n equals to 1, since n equals to 0 is not allowed. Because critical load is that smallest value for which buckling will actually occur. So if you substitute n equals to 1 in this equation, you get the value of critical load is pi square EI by L square, and this is the Euler buckling load. If you substitute the value of n in this mode shape, then you get the value of Vx as C sine pi x by L, which is the corresponding buckling mode. So whenever this is the critical load acting on your column, the equation of the deflected shape or the deflected curve will be given by this Vx. So this is the value of your buckling load. You can see that the Euler buckling load is directly proportional to the flexural rigidity of the column and inversely proportional to the square of the length. So the longer your column is, the lesser will be your Euler buckling load. And the larger your flexural rigidity, the higher will be the Euler buckling load. So this is the derivation that we are trying to do today, the derivation of PCR. Now you can see here what we were discussing previously about the mode shape or the deflected shape or the buckling mode. So this is our undeflected column. If we have applied the load up to this value PCR1, that is our critical load, pi square EI by L square, we saw that our deflected shape was given by C into sine pi x over L. So this is our first buckling mode, n equals to 1. If we increase the load beyond this value of PCR1, let's say for the second buckling mode in which n equals to 2, then n square gives you 2 square, which is 4, and this is the critical buckling load. In this case, this will be our deflected shape. You can see here the deflection is 0 at the center and it is deflected into two curves here, separate curves. But remember, in actual, this deflected shape rarely exists, since on reaching this value of critical load, already we have got this deflected shape. In order that we get this second buckling mode, what we can do is we can just apply a force here such that there is no deflection at this point, and in this case we can increase the load up to this point and get this particular deflected shape. But in reality, this is not applicable, rather this is the deflected shape that we get. Now after determining the buckling load, you can determine the buckling stress also, which is given by load upon area. Now here the value of moment of inertia is given as AR square, where R is the radius of gyration and R is given as root over I by A. If you rearrange these terms, you will get the buckling stress as pi square E by L by R square. If you remember, this L by R is the slenderness ratio of your column. Now again we see that the buckling stress is directly proportional to the modulus of elasticity, but inversely proportional to the square of the slenderness ratio. To exhibit this variation of buckling stress according to E and L by R, there is a simple graph that I have taken from this book, Mechanics of Materials by Roy R. Craig, that shows the variation of L by R and sigma CR, which is the critical buckling stress. You can see that since the graph has been shown for two types of materials, steel and aluminum, since steel has a higher value of E as compared to aluminum, for the same value of L by R, you get a higher buckling stress for steel, since this curve is above the curve for aluminum. So, using a material with a high value of modulus of elasticity increases the value of critical buckling stress and the critical buckling load also. And remember, although not shown in our derivation yet, this equation for buckling stress and buckling load is only applicable to the limiting stress of sigma y, which we consider as the compressive yield stress. Above the value of sigma y for any material, either aluminum or steel, this equation is not applicable. So this shows us the graph of Euler's formula for structural steel and for an aluminum alloy. So this is about the derivation of the equilibrium of buckled column, in which we derive the value of the critical load and the critical buckling stress. So in today's lecture, this much is what we are going to talk about. We derived the equilibrium equation for an ideal column. In our next lecture, we will see what happens when these ideal conditions differ. So we'll meet again soon in our next lecture. Till then, stay safe and thank you.